Good morning, I am Laurie Conteville. I am a lecturer at EFREI Paris in France. I'm going to present the article Study of Irregular Constellation of RFID tags for indoor distance estimation that we submit at MENACOM 2021. This is the work of Yiman that she did during her internship at EFREI Paris. Elisabeth, Colin and I were her supervisors. Indoor localization has the same purpose as outdoor localization. We want to estimate a position, but inside building, hospital, mall, airport, etc. Outdoor localization is a well-known topic. For example, the GPS is very efficient nowadays. But for a good estimation position, the measurement should be the line of sight between the subject and the satellite. In the context of a big city, there is still a problem to estimate position because of buildings and small streets. This is called the urban canyons. There are non-line of sight signals, refraction, diffraction, etc. because of the environment. Using GPS for indoor localization, the power of the signal measurement is very low, so we can't use this technology for an efficient position estimation. Moreover, the received signals are very weakened due to the strong attenuation of the walls. Metrics such as received signal strength, angle of arrival or time of flight are not directly related to the distance or relative position between transmitter and receiver. This is due to multipath phenomena, which can be dominant in indoor environments. There is no standard solution equivalent to GPS indoors. Literature shows that multiple antenna systems reduce multipath fadings and improve spectral efficiency. Indoor location can take advantage of it, improving the accuracy. Recently, indoor localization based on multiple input, multiple output, and massive MIMO gives good results, with a symmetric positioning in small areas around few square meters. This high accuracy is achieved at the cost of a complex device. A low-cost, multiple input, single output using signal strength only and performing symmetric positioning, validating the constellation principle for distance estimation. In this work, we use constellation of 4 tags as the best numbered tag, and we study regular and irregular constellation. A constellation is multiple tags close to each other. The best regular constellation is a diamond shape where each tag is at the same distance from the center. The position tags are 10 cm to 50 cm from the center, with the step 10 cm plus the radii 70 cm and 1 meter. Then we have 7 different radii. Irregular constellation is made by 4 tags from these 7 radii. In this paper, we optimize the tags placement in the constellation, thus proposing new irregular constellation for higher accuracy. Position estimation of a subject uses the distance estimation from multiple tags. Here we study the distance estimation of one input made by not only 1 tag but 4 tags, the constellation. We use the RSSI, Received Signal Strength Indicator, for the distance measuring. As the signal channel, we use the one-slot propagation model, which is the reference model in the literature. The model is described as power in dBm in terms of the distance given by the first equation, with P0 the received signal strength at the distance 1 meter. The measured power is calculated with the RSSI to dBm constructor correspondence graph, second equation, and the RSSI is the received signal strength indicator, which is measured by the reader, The distance estimation is given by the third equation with n the path loss coefficient that describes the signal attenuation in the environment. Moreover, we define the estimated distance error as the real distance minus the estimation distance. The experimental setup is the following. The environment of the experiment is performed in a classroom at EFREI Paris. The furniture and standard objects were removed in order to limit the interferences and the reflections. There were still some metallic objects, such as heaters, writing board, and metal grid, which cannot be removed. RFID equipment tag. The system works at 433 MHz. For active tags, UHF RFID tags. The reader and tags are both from ELA Innovation, and tags detection is around 20 meters in an indoor environment. The RFID tags were placed in the constellation form on the wooden board hanging vertically on the wall. We worked on 7 different constellations ready, from 10 cm to 50 cm by step 10 cm. We took additionally ready 70 cm and 1 meter. The reader is aligned in front of the wooden board. It is placed on cardboard boxes in order to avoid reflections of the signal received on them. The RFID reader was placed at 1.26 meters high. In the first scenario, we use 4 tags in regular constellation for measurements for 7 different radii. The shape of each constellation is a diamond placed on a circle. The center of the constellation is the center of the circles at 1.26 meters high, at the same height as the reader. Measurements were realized following a linear path in front of the center of the wooden board from 50 cm to 80 cm with a step of 50 cm. For each reader position, 230 RSS measurements were performed per tag and per antenna. In the second scenario, the constellation is made of 4 tags, putting them randomly in an allowed position in the 7 circles, thus forming irregular constellations and regular constellations. The shape of constellation can be either a triangle or a quadrilateral. We analyzed 10,000 irregular and regular constellations out of the whole computed. Constellations were assessed considering its area and the sum of distances from the tags to the barycentre of the constellation. We observed that the smallest is the constellation. In terms of sum of distances like barycentre, the best is the mean error of distance estimation. We also find the smallest errors at the boundary of the curve, which corresponds to the regular constellations. For these 2 constellation shapes, small irregular constellation and regular constellation, the mean error of distance estimation is less than 2.5 meters. Moreover, this figure shows that for most small constellations, area less than 0.25 square meters, and regular ones, the mean error is less than 2.18 meters. This value is the mean distance error obtained for the regular constellation with radius 70 cm. That is the best irregular constellation. In this figure, we consider 7 constellation samples. The first sample corresponds to the constellations with some of the distances tagged barycentre lower than 0.5 meter. The interval for subsequent samples is 0.5 meter up to 3.5 meter. For each sample, this figure presents the percentage of constellations with better accuracy than best regular constellation. Finally, we have more than 50% of the constellations for 4 first samples, less than 2 meter and less than 0.45 square meter. The second sample of constellation 0.5 meter to 0.99 meter, and the maximum area is 0.1 square meter. This sample presents the best percentage of accuracy with 68.8% of them that better perform than the best regular constellation with the radius 70 centimeter. It confirms that the bigger the constellation is, the biggest is the mean error of the distance estimation. As perspective, more investigations are required for a deeper analysis of the regular and irregular constellations, studying the cumulative distribution function of 90% and the standard deviation. Further work is to implement algorithms to automatically adapt the constellation for a given environment. Thank you for your attention.